my name is Scott Meredith Jones. I'm a control and automation engineer working for Control Techniques R&D. In this video I'd like to introduce a useful new motion control interface called PLC Control Motion. Let's check it out. So Control Techniques drives are often used in control systems with a central control PLC from a third-party vendor, so something like an Allen Bradley Rockwell or a Siemens PLC. Control Techniques has classically had a connect to anything philosophy, so we've supported lots of third-party vendors' communications protocols, so things like Profinet, Profibus, DeviceNet, Ethernet IP. Because we recognise that a lot of our system integrators and OEM type customers quickly want to be able to integrate with these third-party PLCs, we needed a better PLC side integration with our product to help those customers to be able to achieve whatever motion that they'd like to do for their particular system quickly. So what is PLC control motion? Well, it's a set of application integration tools that allow third-party PLCs to command and control a Control Techniques drive to generate a range of motion control functionality. So the offering itself splits into three categories. So we have a guided setup tool, a comprehensive set of PLC motion interfaces that are actually available inside of the PLC environment for the third-party product, and full step-by-step guided documentation for the plugin called PLC Control Motion for Connect. So once you've actually installed the plugin, which we'll cover later in this presentation, PLC Control Motion can be selected under the Setup menu within Connect. The first screen that you'll see is the Axis configuration screen, which allows you to gain access to the main system preferences. So first of all, selecting which PLC type you'd like. So the first offerings will offer you Rockwell PLCs controlling over Ethernet IP comms protocol, and Siemens PLCs controlled over Profinet protocol. Second thing you'll get to choose is the control type. So there's 5 different motion interfaces, if you like, that are available to you within the PLC that are configurable from the drive side using this tool. So anything from a simple frequency setup in open loop, closed loop in RPM units, and then 3 motion controller based motion interfaces. One that's a simplified speed control interface, but in real engineering units. So whatever user unit that you'd like to choose. So that could be I don't know, millimeters per second, something like that, or sorry, millimeters per millisecond. A position control interface that gives you sort of indexing type capability, and lastly an electronic gearbox interface. So that gives you the ability to follow a real-time motion reference over synchronous communications. Lastly, the machine type. So we've got 6 different machine types. So we have 3 that are a rotary type machine type, so standard gearbox ratio, belt and pulley, and worm drive are all rotary machine types. And then you've got 3 linear types, so that's ball screw or linear slide, because they're very similar sets of mechanics, rack and pinion, and conveyor. At any time when you're using PLC Control Motion, the documentation and all of the PLC code, all of the example code to show you how to get things working are available by clicking on Libraries and Documentation. And you can see that you've got a good range of documentation under there that's all step by step. So after completing the Axis configuration, the next thing that you're presented with is the motor selection. Okay, so you can select a servo motor, you can select an induction motor. Servo motor happens to be shown here. One of the nice things about this particular page is not only can you enter things in directly if you've actually got the motor nameplate details in front of you, but you can also search using the database function here. So in a case of servo motors, you can search using the standard product name for a Control Techniques Dynamics motor, or for a Leroy Somer motor, you can simply search in here and then bring up the details for your motor, click, and then those details will be promoted to the motor nameplate area here. Next, we've got the option module section. So in this case, because this drive is a Digitax HD M750, it has 2 option slots plus onboard communications. So here you've got the ability to add an additional communications option, digital I/O option, or an additional feedback interface if you were doing something like a dual loop setup. So after the motor setup and option module setup, you've got encoder setup. So depending on your configuration, you have a number of properties that you can sort of set up for your encoder. So you've got supply voltage, a number of lines per revolution, etc. You've also got the ability to set up a dual loop system. So that's one where one encoder controls the speed loop and another encoder controls the position loop. Okay, so this is for the AMC motion control type motion interfaces. You don't have this kind of setup for RPM type axis or frequency control type axis. Other things that you've got under here are things like freeze position capture. So if you want to know with a high precision the position of the axis, so you're doing like a custom homing routine or something like that, you've got that capability here, and the configuration for that is in this tab. So then you've got the machine setup. So in this case, you can see that we chose standard gearbox ratio, which promotes the gearbox setup tab to appear. So for this particular machine type, you can configure the method that you'd like to enter in your ratio. So it could be teeth in to teeth out, input speed to output speed, turns in, turns out. In this case, this is input speed to output speed. Okay, but this tab basically changes according to the mechanics that you've selected, and then you'll be able to, set up the appropriate parameters for that particular machine. Hardware limits. So this page essentially sets up the hardware limits for the motion controller. So it's saying you're going to go and connect a 24-volt signal from some sort of hardware limit, which could be a switch, something like this with a roller cam lobe on it, and then assigning it to be a forward positional limit or reverse ultimate positional limit. Brake control. So there's 2 forms of brake control assessed on this particular page. You've got electronic brake control, so that's handling of DC energy from regenerative braking. So you've got the ability to set up the resistor power, etc. And you've also got the ability to set up mechanical brake control. So that's automated clamping of the axis motor when you've disabled it, for example, to prevent load from dropping. So if you're doing some sort of hoisting application, then you've got the ability to configure the brake controller for that type of application here. Network inputs and outputs. Note that for Siemens products, or Siemens PLCs, these 2 tabs don't appear, so this is exclusively for Rockwell. So for Rockwell, you've got the ability with the network inputs and output tabs to be able to user-define 4 cyclic inputs and 4 cyclic outputs. So it allows you to sort of customize the data flow to and from the drive for any additional information that you might need to service your application. So when you go to set it up, simply add the parameter numbers that you'd like to get hold of in these setup boxes, and those will either go to the drive or come from the drive. User units. So this is where you configure the type of unit that you're interested in. So there are various rotary units. So in this case, this is set up with a rotary axis because it's a standard gearbox ratio, so it's only rotary. And so we've got a standard set of engineering type units here. So in this case, it's degrees. Obviously, degrees is quite a coarse unit per revolution compared to most encoders. So a lot of encoders are capable of giving something in the order of 16-bit or 65536 counts per rev. So to allow the user to be able to easily configure extra resolution to make the most benefit of the encoder that they've got fitted, you can say how many decimal places of resolution you'd like for one of those units. You've got the ability to configure and set up the slave position feedback here, and you've also got the ability to set up speed restrictions, so things like what's the ultimate maximum speed that you'd like the axis to be able to go to, or what is the maximum speed that you'd like to be able to apply to correct positional following error. RTMOE setup. So RTMOE is IEEE 1588 based synchronous comms protocol that Control Techniques use. It's used to transmit and receive real-time encoder data as a means to be able to cause an axis that's set up as a position control axis to send out its position as a reference for another axis to follow. So the following axes are always EGB, electronic gearbox axes. So the idea is that you could have something like a multi-section conveyor system where the conveyor at the start of the system is in position control because you're trying to position the product, and every successive conveyor belt after that is following that position motion interface's position reference, so that they all flow together all at the same speed. So homing, there are several different homing routines built into it. The hardware side, so the drive side of all of these different homing routines, is configured from the homing tab. So as you can see, this particular setup is for homing on a positive limit, where the positive limit is indicated by a hard stop. So this is typically for a linear type axis, where what you do is you drive very slowly into the ultimate physical limits of the axis, and at that point use the forward limit as the home or datum for your system, so that you don't have to take the cost of a sensor. You can just use current sensing to know that you've reached the end of your travel. Okay, and that's it. At the end of that setup, you would then go and apply that, download the settings to the drive, perform an auto tune, and then you'd move over to setting up the PLC side. So the standard AOIs, or function blocks, have been designed to meet the needs of most applications. The interfaces themselves can be edited to a certain degree to allow you to build in customer functionality. So for example, the interface that you see here can be fully edited internally if you'd like to make a custom implementation. Ladder logic is used wherever possible, just to meet the general customer need, really, and to make it easier to debug. Rockwell PLCs are supported from version 17 of the Rockwell firmware, and Siemens from TIA portal version 14, specifically S7-1200s and S7-1500s. Cyclic comms can be updated as slow as 100 milliseconds and still achieve nice synchronous motion if you are connecting something like a positioning axis to an EGB axis, because the synchronous communications between those is handled actually at the drives rather than via the PLC. So what that means for you is that you can use a relatively low-end PLC and still get relatively high-end synchronous motion between two axes. So, as we said before, when we were looking through the drive setup tool, there are 5 main function blocks available. So we have a frequency, open loop frequency operation interface. We have a speed interface that operates in RPM units, so it's closed loop. We have speed in engineering units using the drive's onboard motion controller. Positioning in engineering units, also using the drive's onboard motion controller. And electronic gearbox, also in engineering units, using the onboard motion controller. Example routines are provided to help the user get going with all of these different motion interfaces, regardless of the third-party PLC used. There's examples for everything in there to get you going. So there are a certain number of supporting function blocks to help you build a system. So for the Rockwell environment, we've got non-cyclic comms read and write blocks, so that you can, instead of using cyclic communications which have a fixed destination, you've got non-cyclic comms that you can direct to any parameter that you like within the drive to receive parameter information, for example, at any point in time rather than cyclically. But for all of the PLCs, we've got dedicated digital I/O read function blocks, drive status function blocks, and AMC status function blocks if those items are useful to you. So the function blocks themselves have been categorized. You can see we have 3 different prefixes for each of the different categories of function block that are available to you, or AOI. So things that start with the prefix CTA, they're primary motion functionality. Okay, so these function blocks here, so electronic gearbox, frequency hertz, position AMC, etc., etc. So those are your main motion functionality. CTB, so things that are marked with CTB, those are auxiliary type functionality. And things that start CTC, they may be useful to you, but they're mainly intended to be system underpinning functionality. Okay, so they're not really intended to be used. Some of them might be useful to you because there are things like limit function blocks or AOIs and so on, but you're not really intended to use these. So the idea is that you can go straight to the function blocks with the prefix that you're interested in. This is not such a problem for the Siemens environment, but certainly for Rockwell, if you're using the earlier versions like version 7 of the Rockwell environment, the way that it structures the AOIs, it does it in alphabetical order, so having this CTA, CTB prefix at the beginning just makes it so that you can actually gain access to these rapidly. So the AOI or function block structure is such that we have an outer layer. Okay, so the outer layer are these function blocks or AOIs in the Rockwell environment, and then those give you an interface to an inner core of functionality. So this inner core of functionality is always visible, but is not editable to make to keep it maintainable. But the outer layer can be fully edited and investigated. You can do what you like in this layer, basically, just to add a certain amount of flexibility for customers using this. So the function blocks themselves, the inputs and outputs, have 3 main categories. We have inputs that start CMD. So CMD is command. So these are typically Boolean command inputs. So it's for things like drive on, so that's enabling the drive, enabling the motion controller within the drive, resetting the drive, calling a motion stop or a jog, etc. So CFG, which is configure inputs. So this is setting up the properties of an individual reference. So for example, you can see down here we've got configure jog speed, jog acceleration time, jog deceleration time, etc. So configure inputs are there to set up the properties of these commanded reference. And last of all, status outputs, which have the prefix STS for status. So we have a number of outputs available to you, so you can monitor profile input speed, profile output speed, following error, etc. as part of your process control. But we've also got Boolean outputs so that you can arrange your sequencing. So for example, if you have turned on jog forward and you want to know that the axis is actually actively jogging, you can check status jog active, so as part of your Boolean sequencing. So onto the motion functions themselves. So first one is called CTA frequency hertz. This one works on the entire current AC drive range, so it works on the commander range, Digitax HD and Unidrive M, because all of them support open loop control. Has a dedicated motion stop reference, a jogging reference for manual control, and then a running reference for automated control, so you know when you're running your process from a program. Next up the scale, we have CTA speed RPM. So this is a very similar looking interface to the frequency one, except for now this is in closed loop, so you have better, stiffer shaft control. Again, motion stop, jogging reference for manual control, running reference for automated control. The one thing to note here is that this particular interface and all of the further ones that we're going to mention aren't supported by the commander range because those are open loop only drives. So first at the motion controller based ones. So this again is a very similar interface to the one that you saw for RPM, but in this case we've got position control, so we've got a closed speed loop and closed position loop, and it's in engineering units, so this could be any kind of speed unit or speed unit that you'd like. So that could be, I don't know, millimeters per second units, something like that. It's got a dedicated motion stop reference, dedicated jogging reference, and speed reference for automated control. CTA position AMC, so this is a positioning motion control interface. Works with Digitax HD and Unidrive M700 and 701, etc. Motion stop reference to stop the axis, jogging reference for manual control, homing reference for positioning and setting up the axis for starting, and 10 selectable position references, which can be either absolute or relative type moves, or for indexing type applications. Again, closed speed loop, closed position loop, and you have the ability to separate the loops with this and the previous speed one if you want to do a dual loop type setup. Last of all, CTA electronic gearbox AMC. So this is a EGB or digital locking function block, or AOI, where it's Digitax HD and Unidrive M70X. Motion stop reference, jogging reference, homing reference, single position reference, so you haven't got 10 individual ones like the positioning reference, but you've still got the ability to dynamically position the axis if you want to. And then last of all, an EGB reference with a PLC selectable position master encoder over our IEEE 1588 RTMOE synchronous communications interface. And again, closed speed loop, closed position loop, so you've got very good shaft control there. So a summary of the benefits is essentially significantly reduced integration times compared to our previous offerings. Before, if you had to go and set up individual tags for each of the features that you'd like to use in the drive, that could take you quite a lot of time. So as you'll be able to see in the demonstration after this presentation shortly, if I wasn't talking and describing around the things, I'd be able to get an axis going through the drive configuration side and the PLC side and get the axis jogging in approximately 5 to 10 minutes. It would be very quick. You wouldn't have been able to do it that quick before. You have relatively high performance motion, so you have the ability to make an electronic line shaft type system, for example, using the EGB function block with a relatively low spec PLC. So example, you could use something like from the Compact Logics range in L24 and end up with synchronous motion between two axes, even though that PLC itself doesn't natively support synchronous motion. Same again with the Siemens. If you used an S7 1200, you could get synchronous motion going with that, because all of the motion control parts have actually been decentralized to the drive because it has an inbuilt motion controller. So it means you can make quite a complex system using a relatively cheap PLC. Only one network required, standard Ethernet. Okay, so the IEEE 1588 RTMOE communications plus your PLC communications all go over a single Ethernet connection cable, so it's quite simple to wire. You've got simple migration between different third-party PLC products. Okay, so because the motion interface is common between Siemens and Rockwell, and so is the drive, it means if you've got a customer base that generally swaps between Siemens or Rockwell type systems, as those are some of the main players for third-party PLC products, you would only actually have to learn one motion interface and be able to work with both of those systems and not really have to learn anything new, because it's a common interface between those two PLC environments. One thing to note is that if you do have a system and you're working with Siemens and Rockwell, then the M700 or M750 Digitax HD drive, when fitted with the multi-protocol factory-fitted Ethernet module, that particular drive is able to work, over the Profinet Ethernet communications, and it's able to work with Ethernet IP communications. So no matter which PLC that you're working with, really you only need one drive there to be able to work with either of those communication protocols, which is quite helpful. It's fully supported, so good training, good documentation. For our drive centres, they have support suites so they can kind of log issues, technical support, and R&D people, like myself, are kind of continually working on this product. It's a flexible product, so there's much of it that's open that can be tailored to an individual application centre or end user's requirements. the support for our current AC drive range, so the full range. And finally, there's no license fee. You know, many of these third-party environments, if you actually want to use their complex motion capabilities, you actually have to pay an extra license fee to add that to the capabilities of the environment. With the Control Techniques offering with PLC Control Motion, you can just use the standard PLC environment and be able to gain access to this, provided the PLC that you've chosen supports Ethernet IP or Profinet. Okay, so the next phase of this demonstration is to show you some hardware and some physical setups in an end-to-end demonstration. So let's move to that.